Oh, thank you for watching. And I wanted to go over this topic, talk about simplifying radicals uh, that have negatives underneath them. And first idea goes back to just in general, how do you simplify radicals? So that idea is kind of in two directions. If I had something like this, the square root of 24, I could simplify that any number of ways. I could say that's the same thing as the square root of 12 times the square root of 2, the square root of 4 times the square root of 3, square root of 6. I'm sorry. I am sorry. We're going to pretend that I didn't just completely get ahead of myself here. I should think about just one thing at a time. So 12 times 2, square root of 8 times the square root of 3 would be 24. And the square root of 6 times the square root of 4. So square root of 12 times 2, 8 times 3, 6 times 4. These are just factors of the number 24. So I can separate it out any number of ways. And so that's the first thing that's from previous examples that will come in handy. Now, along with that, I can go in the opposite direction. So if I had 12 times 2, I could simplify that to 24. If I had 3 times 8, I could simplify that to 24, or 6 times 4. So I can go either direction, and that goes for multiplication or division, as you'll see here in a second. So the first thing I see here is square root of negative 13 times the square root of negative 7. And so there are various ways to go about this. The first thing I can do is to take those two numbers and multiply them. And as far as 7 times 13, that is 91. But I have to keep in mind I have a negative times a negative. And so will my answer be negative or positive? And the answer is positive. So this is what I'm left with, the square root of 91. At this point, because it's a positive number, I can go about the process that I described earlier, where you are looking for a way to separate and find factors of 91. But there are some factors that are more useful than others. And really the only ones that are useful to us are called our perfect squares. So those numbers are 4, 9, 16, 25, 36, 49, 64, 81, 100, and so on. Those are perfect squares because I know the square roots of those. They are whole numbers. So that's why those numbers are helpful, is because when I simplify them, I can simplify them just to a whole number without a square root sign. So what I'm looking for is, are there any of these numbers, 4, 9, 16, 25, 36, 49, any of those numbers that would go into 91? And you can simply take a calculator and divide. 91 divided by 4, and it does not go into it. 91 divided by 9, it does not. 91 divided by 16 does not. So as I go forward, I will notice that there are no numbers that go into that, and so square root of 91 is as far as I can simplify that. Now, these numbers right here, square root of negative 63 times divided by the square root of 9. The nice part is I notice that right there is one of my perfect squares. And so I can automatically simplify this to that right there. And then I can go through that process. What I'll notice as you go through this process, there are various ways to go about this. And so if you have a different technique that you use, that is totally fine. Now, as I think about separating the 63 out, what I notice is that 9 goes into 63. 9 goes into 63 7 times. And so what I can do is I can separate this out into a 9 and a 7. One thing I have to keep in mind is this negative. Negative. how do I take care of a negative under there? Normally, I cannot take the square root of a negative number. Okay? It is not a real answer if we use our definitions of what a real number is. So we have imaginary numbers. Now, it sounds like something that would be made up, but imaginary numbers are ways that we can take square roots of negative numbers. And so the definition of an imaginary number is the square root of -1. So you'll notice I took that negative and treated it by itself over here in order to account for it. So 63 is the same as 9 times 7, and then this took care of the negative by making -1. Now, am I able to simplify these? Yes, this simplifies to a 3. Square root of 7 does not simplify. Oops, does not simplify. And then the square root of -1 we said is an imaginary number. And so I'm going to put an I here to represent that we have an imaginary number. And then I still have the divided by 3 on the bottom. So what you'll notice is that I can actually, normally this may be a final answer, but I do notice that I can simplify one more time. 3 divided by 3 is just 1. So they basically cancel each other out. And what I'm left with then is that imaginary number times the square root of 7. So that's how you handle it when it's a negative number. A second process you could go through would be to actually divide early on. If you took 63 divided by 9, 63 divided by 9 is 7. Well, -63 divided by 9 is -7. And now we could do the same process and simplify this to square root of 7, square root of -1, and I would end up with the same answer. Imaginary number times square root of 7. So that I just represents that we had a negative number underneath there and that we have an imaginary answer. Okay, I'm going to clear that real quick and then just look at a couple other examples. Oops. So we'll try that process we had just talked about. Let's see if dividing early on makes it simpler for you. So -66 divided by -6. Well, negative divided by negative is a positive, and 66 divided by 6 is 11. So I'm left with the square root of 11. And as I think about these numbers, 4, 9, 16, 25, 36, and so on, none of them go into 11. And so you're left with that as a final answer. Now this right here, square root of -5 times square root of -20. Again, negative times negative is positive, and 5 times 20 is 100. Square root of 100 is just the number 10. So that one worked out fairly easy because it ended up being one of my perfect squares when I multiplied. Hopefully that helps you in determining how to simplify these radicals. Sometimes you have negatives in the end, sometimes you don't. And that's where those imaginary numbers come into play. But if you have questions, please let me know. Thank you so much.